First of all, a very warm welcome to all of you. It's really been my pleasure to kick off this inaugural session of this joint seminar series between IIT Delhi and Johns Hopkins, which is going to be a seminar series on scientific machine learning. And we are truly excited to launch this collaborative initiative between the two universities with the aim that we will bring together researchers at the intersection of machine learning, physics-informed modeling, and engineering sciences. So this seminar series was intended, or rather we had been thinking about this for a couple of months now, and it's intended to be a space for intellectual exchange where we hear from the leading voices of academia as well as industry experts, and we discuss new directions. And so we hope that these sessions are actually going to be providing us that. And we'll be hosting these sessions every Wednesday evening in the Indian context at 7:30 at the Indian Standard Time. And we hope that many of you will be actually become our regular participants. So with that, now it's time to introduce our speaker, our first speaker, Dr. Syed Alam, who sets quite a high bar for what the seminar is supposed to offer. So Dr. Alam is an assistant professor in the Department of Nuclear Plasma and Radiological Engineering at the University of Illinois, Urbana-Champaign. His research focuses on digital twins, virtual sensing, and the use of scalable machine learning in complex energy systems, a topic that falls right there in one of the themes of our seminar series. Today, he's going to speak on scalable digital twin enabled virtual sensing, and he's going to talk more about it. With that, Dr. Alam, the floor is yours. Thank you once again for being a part of this launch. Over to you.
Thank you, Professor Naik, and thanks, Professor Chakraborty, for inviting me. When I got to Professor Chakraborty was actually like a Fulbright fellow in the university at the University of Illinois Urbana-Champaign, and we are very, very excited and lucky to have him. In fact, I think we were stuck. Our group was stuck in in thoughts in which direction we should really proceed. And Dr. Chakraborty actually floated really great ideas that actually we are working on. So I really want to start with that gratitude. Thanks, Professor Chakraborty, for being a good friend. So thanks for the introduction, Professor Naik. So today I will actually mostly talk about scientific ML part, but more from the scalable part, beyond benchmarking, and how it can help in virtual sensing that leads to the digital twin things, and how all these things can boil down to foundation model for energy systems. So when I'm saying energy systems, it's mostly physical systems, by example. Okay. So this is my group, but again, lots of faces changed, and we are kind of it's an evolving group, and I am honored to be the PI for that group, and my lab lead is PhD candidate Kazuma Kobayashi. So he's in third year of his PhD, and other students are also doing great job. And before starting, just we work on actually three main thrusts: scientific ML-driven intelligent digital twins, material performance, and multi-physics. But this thrust 2 is mainly to generate dataset for thrust 1. And when we have this thrust 1 intelligent digital twins, that also boils down to some cybersecurity and system decision making. So robotics is not really hardcore robotics. It's actually the virtual sensing, or actually kind of on-the-fly sensing things. That's in thrust 1. Actually, we work on mostly explainable intelligent AI, and we just started working on foundation models with Professor Chakraborty and some operator learning things. And thrust 2 boils down to material performance and multi-physics, mostly from the CFD part for the data generation aspect. And cybersecurity, one of the aspects, because our main field is nuclear systems, and when we have the digital twins, it needs to be protected by the US Nuclear Regulatory Commission rule, right? So from that aspect, actually, this the cybersecurity actually comes in naturally. So these are our three thrusts that actually we working on. So from the audiences, if anyone is interested, connecting with us, join with us, please feel free to email or reach out anytime. So some advertisements, that's what we do, especially in any, when we go to any university. So it's kind of it's a shameless advertisement, but again, I will follow the procedure. So I will say it's not my achievement, it's actually our group's achievement. And all the results I will show, none of the results has been generated by me personally. It's all by the students. Mostly it's Kazuma Kobayashi's PhD. Okay, so, and through their work, actually, like our group has been part of one of the National Academy Committee member on foundation models for scientific discovery. And again, due to their work, I think our lab has been named as a national AI leader for White House AI action plan under Trump's $500 billion, something like that. The number is top of my head. And also, we have been honored by Salmons Foundation, like as part of one of some stewardess of AI. And there are some other things that actually like we have been privileged to actually like get recognition. And one of the work from our group has actually got some attention. I don't believe that's really a breakthrough. I'm glad that some people misunderstood the work and assumed that as a breakthrough because it's a fairly straightforward work. I think the system is complex, and that makes an edge here. So now I'm actually jumping to the main topic, the AI digital twin for energy or nuclear power systems. So most of our use cases are related to more like energy and nuclear systems rather than the regular like the benchmarking problem. So I'll go there soon. So one thing actually, like when I was giving some talk in some places, some senior professors whom I respect deeply, they were very angry. Not angry, they were actually upset that, okay, so you're saying that all can be solved by AI, like you don't need any domain knowledge. Like, is it so? And that resonated with me. So so that's why I actually kind of get cautious and start with that slide. That no, AI ML is extremely important, but we cannot avoid the domain expertise. We need to have the domain expertise, and based on the domain expertise, we need this AI expertise we need to develop, and then we can work. So without domain expertise, the scientific machine learning field, I don't know what's going to be the future. So domain expertise is much needed. That's how I want to start our like a technical discussion, just to make sure that we are not saying that we don't need CFD. We are not saying that we don't need this and AI gonna replace that. So my whole point would be AI will augment the way we think scientific computing. It's not gonna replace. I just wanted to clear my position at the very beginning. So this slide is from Professor Chakrabarty. Actually, Professor Chakrabarty is actually one of my mentors in digital twins. So I reached out to him during, I think, 2021, during COVID time. So I was looking at actually digital twins paper, and I got in Google Scholar, I got many names. So I thought, okay, this gentleman looks like a friend, and let's reach out to him. So he replied, and we started the journey from there. It was slow initially, but now we are trying to expediting it. So this slide is actually borrowed from him. And this actually gives actually like so far the I think the best demonstration. I searched for lots of digital twin, GIF and image and all. I think this is by far the best I have got. Comprehensive and brief. I've got the sweet spot. So digital twin, when we talk about digital twin, it's just like a virtual replica of a physical system. And ideally, it should have temporal synchronization, right? And when we are saying temporal synchronization, that means we are assuming that it will be in sync. Again, we are talking about ideal, not real here. And we will be actually talking mostly about what's inside that virtual replica, right? Like how to build that and others. So NRC, US NRC, actually, we are very fortunately one of the groups that worked closely with US NRC, that means Nuclear Regulatory Commission, like Digital Twin Project. We just finished the project, I think, last year. One of the part of the project, not the whole project. So NRC has its own definition, by the way. So digital twin doesn't have any global definition. You can correct me if I'm mistaken. But from the NRC's definition, digital twin is a virtual representation, right? Which is matching with Professor Chakrabarty's definition. And it will span its life cycle ideally. And by the temporal synchronization, we'll have updated from the data will be updated from the real-time data, like the system will be updated. And what we're going to do with those data? Those data needs to be used somewhere, right? Those data will be used for simulation, ML, and others. And when we get those results through ML, what we do? The whole idea is to make decision making. Like that's it. NRC or the DOE cares about digital twin just to help them make the decisions. That's it. Like there is like most of the people, I think, people care about science, but from energy domain or energy perspective, digital twins only job is to help human make the decisions, informed decisions, but the final decisions will be taken by the human. Okay, so also we want to make our position clear that digital twin will not make decisions. That will just help in making decisions. So there has been lots of buzz around like components of digital twin, right? But NRC made it very clear through their reports back in 2021 that digital twin has only three components. One, sensors and instrumentation. And through sensors and instrumentation, you got data. And those data will be used for modeling and simulation. And those data, also you need to have data and information management to make sure that you have the well reservoir of data, like in well-structured manner and others. So, yeah, sorry. So when we are saying all this, why AI for energy systems? Like, do we really need AI? Again, in one of my seminar, one professor from different school asked me that, okay, like energy system has been so fine without AI. Like we got all electricity and others even before the AI jumped in. So why we need AI? Anyone can answer that from the audience? So the thing is that actually, like even like in 1980s, 70s, we had a really good electricity, right, in the world. I'm not talking about Bangladesh or my country and all. So why AI? Like what AI is doing? Like what exactly is doing? Again, as I mentioned, AI is not replacing. What AI is doing, AI is trying to minimize the cost through the operation. That's the, and I at that time I really could not answer that question. Like I was giving some answers that the professor was not convinced. Then he actually corrected me that, okay, AI is actually like your operation and maintenance, you need to streamline it. And that's where AI jumps in, right? And what AI is doing, AI is actually capturing some things that people could not capture with the typical modeling and simulation and others. So AI is basically our extra hand. That means now we have two hands. AI is our basically like another layer of hand that actually like expedite actually our life. It's like we had car in 1960s, but now we have Tesla. It's the same thing, but it just makes our life easy. It makes us more lazier, right? So what are the opportunities in AI? And that derived from that discussion from the professor, that why AI is needed. So real-time system monitoring is one of the aspects, right? We had the diagnostic like ad hoc, but we did not have intelligent alerts. We have now, but again, we want to make it more intelligent. And life cycle optimization and changing environment, those are the things actually like remaining useful life, like more accurate. Those are the things actually like I think AI helps in actually achieving. So how the digital twin now jumps in to energy or the nuclear phenomenon. This is actually courtesy to Nuclear Regulatory Commission to prepare that. So I actually like, although I know that Kazuma doesn't like arrows and all, but I think I put that in the last night around 2 a.m. just to make sure that it's clearly visible. It just doesn't make it clear, like it doesn't make it clean, but makes it clear in terms of understanding. So for example, we have the nuclear power plant, the physical system, and we want to make that digital twin guy. And we have the temporal synchronization. And how the temporal synchronization can be achieved? It would be achieved through real-time sensor data. And how the real-time sensor data will come from? Through advanced sensors and instrumentation. That is, things are connected, right? And when you have advanced sensors and instrumentation, You need to have the computing and networking systems, the wireless connection, the way you want to build your connection, right? And that's where if you want to make it secure, people are talking about the quantum algorithm, quantum safety, all these things are the back end. I'm not going there. So when you have the advanced sensor instrumentation and sensor data, that means you have the data, right? You have to put your data somewhere. Data information management is the place we put our data. And when you have the data, now you have everything, right? So you actually now go into the modeling and simulation box where you put a different type of sub box to work on that, all the models and everything you can run. And the recommendation is that actually you can have it for the lifespan. And from the nuclear aspect, digital twin needs to be used only in 3 different aspects. 1, diagnostic prognostic, because these are very important, especially for the advanced reactors that are coming in the market. Operation and maintenance recommendation. And third one is still not there. There are some like discussion around in the air, autonomous operations and controls, but I'm not very clear about the third point, so I don't want to comment on that. So when we started our digital twin and the virtual sensing, all this work, so we were actually working like in discussing closely with the US DOE colleagues from labs and some NRC colleagues, and we wanted to make sure that, okay, like the work we're doing, it's filling the real gap that US is facing. Okay, I think that was like, I just wanted to make it very clear to my students that, okay, like we want to make our work structured according to all the reports that are being published and what are the gaps that has. So they had some technical gaps, from the DOE, NRC and all. And one of the gap is that the right algorithm selection. So one of the chat I had with those folks is that, okay, there are just too many algorithms. Like which one we should use? And that's a fair question, right? And there are lots of legacy data, and there are also, you're saying that we can generate data through CFD and all. Look, how to use those? And also in the power plant, there are like in the earlier days, people used to write in hand all the data documents, right? So that means sometimes people are like at the end of their office hour and just rather than writing 7.5, they wrote like a 2.7, for example. So their data, like, and if you fit those data, obviously you are not getting anything good, right? Like maybe not good. So that's where uncertainty quantification comes in, and real-time update and explainable AI are there. So these are the actually major concerns from the NRC, from the report cover you can see on the left. So now I'm digging into deep now. So obviously our group is not sufficient to cover everything for what NRC wants. This is actually kind of a guideline to the researchers that, okay, what are the directions people should take. Now, in our case, we actually want to cover a couple of aspects that nuclear world need. What are those? The thing is that when we talk about the nuclear systems and all, the major problem is harsh environment, right? Because if we go back to the digital twin definition, we know that it needs to have the temporal synchronization. What does it mean? That means we need sensor. That means if you don't have sensor, you don't have digital twin, right? Now, if you have harsh environment, we don't know whether sensor is going to survive. And even if sensor survives, there are just too many complex layers, right? You cannot really put sensors everywhere. That means there are some places that you need to see, but you cannot just observe the things there. So this is actually like a real problem, right? And it prohibits direct access by human, but human still wants to see what's going on there. And that also leads to the problem, or coming to the problem from limited sensor coverage. And we also don't want to make a sensor jungle, like sensor everywhere. It will, because of all these systems are actually cooled by the coolant, fluid and all. So if you put lots of sensors, your flow gonna be obstructed and all. So you don't want to do that. So we wanted to check whether we can actually do that. So the main 3 questions that actually we are trying to solve is, can we infer some quantities that sensors cannot see? For example, we know that most of the sensors, like even in the US, we bought a sensor systems like optical fiber from Luna. The sensor actually can handle temperature and strain. But in the advanced reactor systems, you need to see the void fraction, fluid flow, and all these things. But sensors cannot do that. Obviously, you can get those numbers from the sensor and put that in some correlation and get those numbers. But again, it's manual. Do you want to do that? Maybe yes, but I don't think that's the future. That's why this AI thing is coming, right? And also, can we actually reconstruct the full solution, like rather than not only where the sensor is, outside of the sensor zone, can we get what's the whole thing going on, like the whole idea, at least to see how the things are going on? And also, human are like naturally impatient, right? So can we really don't want to wait. So can we get those in real time? Because if you want to make a real-time decision making on the fly, then actually can we get those results in true real time? I think that's where the AI really kicks in well. So this is just like an ideology that show that, okay, like we have the sensor, but we want to get things from here, here, or here, where there is no sensor, how to get those information, basically. Like, can we get information from this sparse sensor data? So that's where actually online monitoring coming. Can we monitor that where we don't have sensor? Now, actually, I'm trying to bring the digital twin, the sensor for online monitoring. Again, if you want to do online monitoring, there are some challenges, right? What are the challenges? Think about reactor system or any energy system, it doesn't matter. With the like, it's not like a steady state. Like there are actually like a change of operating condition all the time. That means we need something, if we really want to have online monitoring or the real-time monitoring, we need to have something that can handle the data shift change or data set shift change and those kind of things. Because we can actually train the model in, for example, 900 Kelvin for all the operational parameters, but it can be like a 1000 Kelvin or 800 Kelvin, right? So this shift, obviously, if it cannot capture, I don't think that that will make AI really practical. And also, for this change, I'm talking about dataset shift. If we have to retrain every time, I don't think that will make much sense, right? So that's why actually the challenges come in. And this is actually an example that bottleneck for energy system. So what we have been doing before the operator kicks in, that we had like a initial and boundary condition for one specific like condition, and we train that, get very good results. But in real energy systems, in a minute, we can have 10 to the power 5 or even more, like a operation condition. And you really don't want to do like build every single model for that, right? And that's where actually like some of the so that means we need kind of like the functional type of thing that will actually solve that bottleneck. So what we want to solve or address is the challenges of what we just said, that can we train diverse set of operational condition? So you can ask me that how are we going to know that a diverse set? Because like if you ask actually any energy system people that, okay, like in the nuclear system, they will know that, okay, like the reactor will actually like will not change from from their last 20 years. It's not going to be from like go beyond 800 to 1000 in different modes. So those are the data sets we have to create, right? And then from there we have to start. That's what I will go now. So we tried actually all these different things: physics informed multi-fidelity, data model fusion. That worked well, like great, actually. Like I think those are fantastic work. But for specific virtual sensor and real-time monitoring, we had to kind of like go beyond that to make things a little more practical. I'm not saying that very practical, but a little more practical, that we can make sense out of that in the next 10 years, maybe. So that's the whole idea. So if we have the sensor in the middle, and if we want to get information here, and two types of information: one, quantities that sensor cannot capture, and quantities where we don't have access. That means inaccessible location. Okay, and actually we are also building like Samurendra, one of the students from our group, is building a lab with the heat pipe and the optical fiber sensors to build a system like that. I'll show actually like the mock-up system that we developed. So now before going to the real result, scalability. Like this is one of the things actually I think I want to talk about. So if a 1D heat equation and you have like a real some ML algorithm you develop, that will actually do a really good job. That's fantastic, right? And that's a fairly like a high school equation, so I'm not going there. And sorry. Yeah, and also we know that okay, like a Navier-Stokes is actually fairly like a popular benchmark problem, and we also tested that with the different systems and algorithms and others, and it works well. Okay, so but the thing is that when we are showing those results to the energy systems people or like a veteran people who are in nuclear systems, even in journals, they're saying that okay, this works well, but what about the real system like this? Where you have the like in the reactor system or other system, you have the air water two-phase flow, and you have the inflow rate of like some millimeter minute, and there are some recirculation back, bubble, and all. Can we really capture those? The question is that like we can capture those things in regular benchmark, but if it's a realistic problem, can we capture those? I think this is the question coming from like the energy system experts or even the DOE. DOE or NRC in the US aspect, they are not looking for real AI, especially in the nuclear AI algorithm, but they are looking for something that solves those kind of problems. So even to make it worse, for the molten salt type of reactor, like there are like the FLiNaC and helium, like as a molten salt, like a coolant, that's make it even like the what is crazy. Like the CFD and those kind of things takes ages. And I don't know any viable machine learning actually gonna work here. So one of our students, Farid Ahmed, is actually developing the use case for that, and Professor Chakravarti is actually is a collaborator for us. So we'll see how to capture those factors. So the point I'm trying to make is that scalability, like issues or challenges, can you capture those things with scientific machine learning or whatever the algorithm you're talking about? So we started with some complex problem, like tried to complex. It's still a toy, but complex with regular. Like we started with very fundamental, like a vanilla deponent, like without any change, and others to see like a shielding, reactor shielding problem. Like we have the concrete and air, and we want to see that if we have the neutron source, how can we make it map to a special flux distribution over the systems? And what we did in the source, we generated like 10 to the power 5, like a energy dependent, like a density, and trained upon that. And we used like a Monte Carlo code fits. It's a transport code, and generally it took like 34 seconds or something like that for one simulation, very small, like simplistic. And Deponent actually kind of did a good job. And again, it was our first work back like in 3 years back. Yeah, I think it's not 2025. I think the reference is wrong. So the inference time was actually good. But again, like it's like you can see, it's just like a regular grid, like rectangular and others. So like operator really didn't have like much trouble to capture the things, but at least all we can say that okay, we at least know that okay, like the flux over the system, even if it's not completely accurate, we have an idea that okay, like these are the flux that will look like this. Because when we're talking about the energy systems, it's actually a pass or fail. That means if we know that okay, this is the margin, it's crossing, that's a problem. If it's below that margin, that's fine. So although in most of the disciplines, accuracy is important, nuclear also, but in energy, it's more about failing or not failing, right? Or close to failing. So at least we can get an idea that where it's going on. And this work has been important because of this work actually gives some idea about like the protection for the worker and equipment, especially the people who works on actually close to neutron source run, and neutron flux actually kind of gives them an idea that how the things are going on. And also, we wanted to do some little more complex things. I'm not saying that it's highly complex, but more complex than like the previous one. So we want to see like how the fluid and the coolant and those kind of like the fluid works, and can we really capture those kind of like a Brownian movement, not literally Brownian movement, but kind of like their flow and others, their composition and those, and actually like our lab has been developing like some operator, but actually more on the multiple input and multiple output side. And one of the paper actually we tried to publish, I think last year, is this is actually just a pipe, but the problem is that actually there's a band, and we cannot actually have sensors in those kind of band, right? But still we want to see what's going on there, right? And the way actually we actually expand it is we have the single input, but the multiple output. So in the trunk, actually, we actually added like 3 layers to get actually like 3 parameters that are not actually captured by the sensor. That means like unmeasurable parameters, like the velocity and all these things. So we have done that in ANSYS commercial one, and the fine volume simulation time took actually like around like 200 seconds, and inference time was actually like order of magnitude lower. But still, there's a catch, because this algorithm worked well as long as the turbulence is lower. That means the lower Reynolds numbers and all. But the moment Reynolds numbers are too high, the things went actually pretty out of control. What does it mean? That means this is not actually the silver bullet, right? So it works when the turbulence is kind of manageable, but when the turbulence is actually kind of in the transient side, this model just pretty much failed terribly. Okay, so it's not the solution of everything. So that also gave us some answer that, okay, this works only in those Reynolds numbers and the turbulent condition. But if we have to go beyond that, it doesn't work well. And so actually, it's also we are working with Professor Chakravarti here in this paper. Professor Chakravarti is a student, and us, we are actually preparing the manuscript. So that's why actually we didn't put any link here. So it's actually what we are trying to do. In the previous work, it was single input, multiple output. But again, single input and multiple output, when it goes above some real numbers, it really doesn't work. So from that, we wanted to see, okay, if we have the multiple input, which is more realistic, and the multiple output, which may be more realistic, can we actually make sure that each sensor is encoded separately through some branch network, and also we can have multimodal data and those kind of things. So from that, actually, we are trying to demonstrate in actually how the coolant flow. And although it looks very simple, but the coolant flow in the reactor systems is actually it's actually one of the most important parameters to look at, especially the subchannel, because this blue thing is actually the water, and the green things are actually the fuel rods, right? And the water circulates there to cool the fuel after the fission and all. So we want to see whether we can capture those phenomena well, because if we can capture those phenomena well, then we know that, okay, the cooling requirement others. And you know that in the Fukushima, the main accident came from actually the coolant, because the coolant was not sufficient that made the fuel hot, and the accident happened. I'm laughing though, but it is serious, right? So with the help of Professor Chakrabarti and some other groups, we actually did some benchmarking, and we got some favorable answer. We are still, Kazuma is still writing the paper. We are there. Hopefully it will pass through. We submitted the work, but the editor gave us some correction. So that's where we are actually expanding the work upon now. And this is actually kind of like a high resolution to see that what's going on. So we the multiple input, we gave temperature, inlet, and inlet velocity. And we want to see the outlet velocity, temperature, and turbulence kinetic energy, which sensor cannot capture. Can we capture that in full field solution? But again, the issue is that the good thing is that we can capture, but the issue is that resolution. It gives a good resolution in the center, but the far is actually going beyond the center. The resolution is an issue. So that means the bottleneck of this work is the resolution that actually we plan on also expanding upon. So this actually, we also try to make it more towards the digital twin. It's 2 years back. So can we predict actually a different observation ID in almost in real time with the 3 different input, like the power, temperature, and velocity? to mostly to get turbulent kinetic energy, which is actually like a linear function of turbulence. So we have been kind of successful in capturing those with agreeable or agreeable accuracy. So one thing also that actually came to our mind, and especially like some of the senior folks said that, okay, when we are doing these works, the thing is that we are assuming that all the sensors are healthy, happy, like movies, happy family. They are giving good result, good numbers and others, but it's not the case, right? So there's a sense of degradation because the data is coming, and if you're talking about the digital twin, sensor is actually one of the things that we need to really be aware of. And you can see that if we don't consider the sense of degradation, this would be the degradation parameter for actually the iron, steel, and all in the reactor pressure vessel. And sorry, it is without degradation. And if we consider the sense of degradation, this is actually widely different, right? So for that, actually, we developed the physics-based with the uncentered Kalman filter and others, like state estimation and pattern estimation, to get the RUL prediction, like a parameter, like a framework. And it was published last year, I believe. I think the title has changed. So we actually captured that, and the plan is actually like with those data which are degraded, can we still predict the same thing for the digital twin that has been predicted earlier? So this is actually one of the work that actually we plan on working. So as part of the MIMO network, we also wanted to see more complex problem, heat exchanger for the reactor system. Heat exchanger is actually like inherently complex with actually nearly I think the use case has like millions of parameters and others. So we are still generating the result, and we got some favorable results. But again, I don't want to talk about that much because it's still not published. And since Professor Chakrabarty is part of the work, so that's why I thought, okay, I should show that. But hopefully we'll submit the work soon. So all the things we talked about are good, but not the great, I believe. Time-dependent inputs is actually one of the things that we have been collaborating with National Center for Supercomputing Application, Professor Korich, Professor Diab, Dr. Diab, and all. So we wanted to see that if we have, because operator that we worked on, it just took spatial, not temporal. So if we have the temporal, with some example of dog bone and plastic material and all, it works well. But again, the question is that, is it sufficiently complex? Is it sufficiently scalable? The question is fair, and the answer is no, it's not sufficiently accurate. It's accurate for only these because it's pretty structured grid, structured mesh. But the things, so when things will be amorphous or irregular, this thing might not work, and that's why actually we have to jump in, and that work started from here. So we wanted to make it to a more extreme level. For example, one of the things that like a satellite and others driven. So for example, in the world there are like 12 neutron monitoring station, and from there actually we can get the effective dose and due to the cosmic ray and others. But for example, I'm from Bangladesh. If we want to get the cosmic ray and all the things back in home where I'm from, there's no way, right? We have to kind of because almost all these are actually kind of the countries where they can afford or something like that. But this part and those of the parts, we don't have any station. But still, we really want to see, right? How the exposure and everything is going on. So our student, actually, Kobayashi, actually developed an algorithm based on a sequential algorithm and a neural operator with the time series and different multiple and the single layer of LSTM and GRU and all. So the paper is actually still in the archive, so you can see, and we got good accuracy, and it's actually sufficiently and confidently it can produce the world's radiation dose field pretty accurately. But again, this work is more on the nowcasting. It's not forecasting. Another limitation is that it just assumed that, okay, the prediction field is actually in a specific elevation. We are not changing the elevation at this point. So for forecasting, actually, one of our new students, Jay, He just joined our group. He's now in the road. He's moving from California to Champaign. So he's actually expanding that work to forecasting, like through like some non-sequential data, and to see that prediction beyond the isolated states to get the real-time intervention and others. So he did a good job. So he extended like around like 14 days of forecasting, and with a sufficient accuracy, and he wants to extend that to a month or so. But again, like I think there are more refinements are needed to expand that work, and and we are working on that now. So current and ongoing efforts, so one of the things that actually we wanted to expand upon is Gen AI and foundation models. And also Professor Chakraborty has some good input on Gen AI, especially for the diffusion models and others. We just started the work. We still didn't publish anything in that area. But we need that because like the data scarcity and others, we want to see that how the field reconstructions are like that, and that will give us actually more enhanced view of the system, inside the system and all. So we are actually working on like the latent diffusion model, DDPM. One of the students from IIT Bombay, who was here for the internship over the summer. So he worked on actually DDPM, DDIM, and Professor Chakraborty also mentioned the flow matching. I'm not still well versed of those technology. I have to learn more to make us like a contribution in the real gap. But we started the work, and we are seeing that okay, like we can generate some results from by denoising and others. Is good, but I don't have still like sufficient confidence that as long as you're not writing the whole manuscript, I'm not sure that whether it will work well. But what Sid generated, actually like the flow matching and others, it gave us some confidence. But again, like the use case is fairly straightforward, like a lead-driven cavity. But again, it handles the transient. But I want to see that in more complex systems before I can make any judgment on that. So also Sid made some good progress like on the generated data and the real ground truth. But again, it's still on the process. And another things, all the things we talked about, that also boils down to foundation model. That's why you have seen the title towards foundation model. So like we have the multimodal system, multimodal data set, like the multiple sensors in the real systems, right? And how can we make sure that we have the system agnostic? For example, in the nuclear reactor, we have like the core, we have the heat exchanger, we have the steam generator. We really don't need different algorithms to actually like train all these things. Rather, if we have an unified model that can give us information directly for heat exchanger when we need, or give us information of the reactor coolant system when we need, and also if we want, for example, like fluid flow, it's actually video data, right? So that means some multimodal information. So that's why I actually like a natural progression is actually the foundation model, where we have the multimodal information and we need system agnostic prediction. And cross-domain generalization is one of the major aspects for us. So rather than saying cross-domain generalization for nuclear, it will be more on cross-subcomponent generalization, because in nuclear there are too many components. So different components, actually we want to generalize that thing. So we try to actually generate something. It's not purely this, but it's like more on the virtual sensing on operators. We got some result, and based on that, actually, we will proceed upon that. So we try to actually do some some empirical calculation on the energy efficiency. Also, like this idea was from Professor Chakraborty that like can we get spiking, because foundation models, the memory is like memory utilization would be heavy, right? And also like you might have seen that Trump has actually like did some executive order on the data centers and others. That means those foundation model, if it runs on cloud, I don't know like how gonna be it's practicability, because we have to think about the practicability, right? So can we run those foundation model in the fog level, or actually in the distributed systems, or near the power systems place, rather than putting all the data in the cloud will be very expensive. I don't know whether it will be feasible. So but from that aspect, we wanted to see that, okay, like the fractional memory and the spiking rate, whether it survives or not. So those are the aspects actually we worked on, and this is actually one of the labs we are developing now. But we tried to develop that in my earlier school in Missouri, but I moved and then stopped. But we are almost there. Like Sam Rendro and some of the students are actually helping developing that lab. And this lab idea actually mainly came from my good friend Matthew from Swansea. He was my colleague in France. So I'm kind of following his footprint, and I'm not trying to be innovative here at all. Yeah, we are just trying to see how he did, and we want to modify that for energy systems, or kind of like mock-up systems that we are developing. Basically, hopefully that will be online in a couple of months if things go well. So this is development by Dr. Matthew Boni, Swansea. So if you have more questions upon that, feel free to reach out to him. I think so. I did not put a thank you slide. I think I'm there almost. So I promised for 50 minutes, so I'm done like 2 minutes ahead. So, so I think I made it in 50 minutes.
Thank you so much for the excellent talk. It was really a good, very broad and very visual presentation. I think visual presentations are great to actually give an overview of what these kind of things. Really great talk. Appreciated it. About Matt,
I think we should give the thanks to my student Kazuma Kobayashi. He prepared pretty much everything here.
yeah,
So
congratulations
thanks,
to
Kazuma,
you.
if you're here.
He is there, I think. So yeah, Matt also. I mean, I worked with Matt for some time when I was in Sheffield. Oh. Yes, he was in Sheffield. He was developing this digital twin.
Yeah. So what a small world.
Yeah.
Yeah. Matt has been in also Missouri. Like he spent some days in Missouri. In fact, when I was preparing my UI/UC application, like for faculty position, he's the one actually like proofread everything, because I wanted someone native to read that. And actually like Matt was the easy victim for that. So yeah, so Matt has been great. Matt and Shobhik, those are the people actually that inspired and shaped our digital twin work largely.
Great.
Actually.
So yeah, I'll ask if this audience have any questions. We have probably time for only maybe 4 or 5 questions, short questions. And if you have long questions, please feel free to write to Dr. Alam. He will be more than happy to answer, I believe. So yes,
if you want to email me questions, make sure that you're emailing the questions before August 20. After August 20, the lecture will start. And I don't think like I'll be writing long mail, at least until September, because it's just like too much work after the semester starts.
That's right.
Yeah, but the good thing is that actually I think we made a very good collaboration with IIT Delhi through Professor Chakravarti, and we had a good collaboration with the National Center for Supercomputing Applications. We have some good collaboration with the University of Texas, El Paso on cybersecurity aspect. So we don't have many collaborations, but we have some fruitful collaborations that lead the way well. So and also our group is growing now. Because when I'm moving from Missouri to here, we lost some students for sure because of the funding and all. But we're trying to recover, and things going well nowadays.
Right. So,
any thoughts, any question, any suggestion?
Yeah. So maybe I have 1 or 2 questions. Maybe I can start with those, and maybe others can follow up if they. Maybe we have a shy crowd here, so maybe I can start. So I was actually looking at that PIPE Foundation. Yeah, I think we have a question from Foundation Program. Maybe I'll just ask my question, and then I'll actually have the floor over to the other person. So about the sensor degradation, you actually had a slide on sensor degradation where you used a Kalman filtering to also have the degradation of the sensor being captured.
Let me go there. Yes.
Probably much later.
It's just like some.
Yeah, there.
Last one.
The previous one. Yeah, this one. Yes. So in this case, so you are assuming that the sensor was also undergoing a degradation. So therefore, whatever results it is showing is probably not correct, right? Is
Exactly.
that
So
the concept?
we are assuming actually initially what we assumed that it's under harsh radiation.
Mhm.
Okay. And the harsh radiation is actually impacting the sensor reliability, actually. And
Okay.
from there, actually, we want to see that, okay, the data generally sensor generates when things are healthy. And if it's not healthy, how those data will look like and the aftermath of that.
Which means that you would have actually calibrated the sensor degradation process completely before you would have actually implemented this
Exactly.
data assimilation. I got it.
Yeah.
And you actually did the sensor degradation calibration separately by actually making a degradation data for the sensor, that how it would degrade
Yes.
under radiation.
Yeah.
I see.
Yeah.
Got it. Yeah. So
but the things that actually, it has been, I think I didn't say that here. So it has been done actually for the real nuclear power plant case, actually, like in Missouri, there's a power plant like Amerin. So we fortunately actually got some data, and they didn't have explicitly sensor degradation data. They had some thermocouples, which is kind of sensor, right? So they have the degraded thermocouples things, and those are the actually like benchmarked information we did, because the journal actually wanted some trust on the model itself. So I think that's what we did. But again, the work itself has limitation because it's entirely physics based. Okay, so I think when is a transient and others, we didn't check. It is still purely steady state. So in transient, I'm not sure whether we can capture those things. I think this is actually like an open area for question.
Okay, thanks. So yeah, I see a hands up. The name is Foundation Program. If you could unmute yourself and ask a question.
That's a nice name.
Can you hear me? Yes, actually, I'm sorry about that. So I'm Professor Shubhangi Mansore. I'm from IIT Gandhinagar, Mechanical Engineering Department. So I mistakenly joined from the wrong account. So that's why it says
Thanks for joining.
Program. Yes. First of all, Professor Syed, it was a really nice and informative talk. So I have two questions for you. So
how many?
One is I have two questions.
I heard 20. Okay.
So. So first question is about, so you have shown a lot of work for different applications using scientific machine learning techniques. So my question is, when you start a new problem, how do you decide which is the which architecture to use, or how to embed that physics into the system? So based on your experience, are there any guidelines that have worked for you?
Thanks, Dr. Program. I can see your name, Foundation Program. So that's why I'm saying Dr. Program, your last name. So that's a good question. To answer your question, first, most of the works are data driven. So so far we did not do much with the physics informed or the physics aware, because the type of applications we do, at least my experience says that physics informed is not very well received by the communities, because data driven is the most appropriate one. So I answered your second question, I believe. To answer your first question, that how we proceed. So to answer, for example, if I actually kind of rephrase your question, the question is that why we chose neural operator, for example. The reason we chose neural operator, because if we have to dive into digital twin, what's the first thing we need? Can you answer that?
First, we need to define a problem, and then what we are.
No, we need sensors, right? If we need to make digital twin, you need the sensors, right? Where the data will come. And DOE is there is a big surge on optical fibers, like distributed fiber optic sensors. And how those distributed fiber optic sensors actually give information. It's more functional input, right? Right. So if we use like vector-based neural network and others, what the problem is that it just chops the information. That means you're losing a lot of valuable information. So what's the point of using that like $100,000 sensors. If you need an architecture that can get an input as a function and give also output as a function. So to answer your question, that's how we land in operator. Because all the sensor data for the energy systems are functional. Number one. So that's how we actually dived into neural operator. Second, also in nuclear system, one of the things I actually discussed in my first 10 minutes that we want real-time monitoring. This is one of the criteria. And we want instant decision making. That means you need fast inference. And neural operator does a really good job in that. So this is how we got into neural operator, and we started with very fundamental or vanilla DeepNet. Now the question is that how we selected the use case. So first we actually used use case very simplistic, because first we needed to know that, okay, can we really make sure that we can handle the simplistic problem? When the shielding worked, then we moved to subchannel. When subchannel worked, we moved to transient to LDC, and then we moved towards like more crazier problem, like the weather and cosmic ray radiation and heat exchanger, those. And when we're actually progressing towards complexity, then we saw that only spatial information doesn't help. Then we tried to integrate temporal. That means we move to spatial temporal. Now, when we are done with the spatial temporal, we are seeing that in the nuclear, there are actually like subcomponents, right? So, and that's where actually this foundation model comes in, because all the subcomponents, you don't want to actually like have it like a separate algorithm. And also we have the multimodality. That's how actually we progressed from one to one. And also some of the things are actually not just what we want. It's also funding driven. So sometimes you get funding for something and you have to do that, right? So, and also like I heard about actually like a neural operator initially from Professor Chakravarti, by the way, in 2021 or 22. So, and I was looking for something, because there are so many things, but I wanted to make sure that, okay, like it aligns with my objective. Like it should not be like, okay, I want to do scientific machine learning. Rather, this is my objective, and then how scientific machine learning actually helps consolidate my objective. That's how I mapped it up.
Thank you. That was very helpful. You might get more questions in the email from me.
Rajdeep, there is a question in the chat. Maybe you can read it out.
Yes. So yeah, in the chat, there's a person, I think his name is, just read the chat out. So here is a question for Dr. Alam, that you have mentioned about functional mapping between for spatiotemporal analysis. Could you please elaborate a bit on that? This person is actually doing some study on scientific machine learning, and he's asking the question, are you using universal differential equation and neural ODs to model associated phenomena, since you said that you wouldn't use pins so much? So
yeah, Rainath, you know my WhatsApp. You could have asked me that question, like in WhatsApp. Yeah, so that's a good question. So what's your first question? So spatiotemporal analysis.
Yes, functional mapping for spatiotemporal analysis. Yes.
Yeah, I think I will actually correct the question a little bit. We are not doing a spatiotemporal analysis. What we are doing that if there is any spatiotemporal phenomena, we are trying to capture that. We are not doing analysis here, right? So when we have a system that actually also varies with the space and time, those conditions, can we capture that, or can we infer that thing? That's what we are doing rather than spatiotemporal analysis. I think spatiotemporal analysis is a completely different term I'm not aware of. Okay. To answer your second question, I am doing some study on scientific machine learning. Congratulations. That's a very good choice. Are you using universal differential equations or neural ODs to model? The thing is that neural operator is actually, if you look at the first paper, I think published in Nature Machine Intelligence, that was actually mostly on universal approximation theorem, right? I think that's a pretty like, I think 90s technique and others. So this is actually the base fundamental for like the DeepNet, where actually we have and also like operator, there are actually also like there are some schools also did different type of operator, but we mostly worked on the one with the branch and trunk. what actually take like one take the branch takes the functional mapping, and the trunk takes the special location and others. So universal exploration theorem is actually the foundation of that, and we are not guessing any pin. I'm not saying it's inadequate. It's just I think it's just like not relevant to the type of work we do. It's not like a pin is not adequate. Pin is good. Like I'm not saying pin is not good. It just doesn't. It's like noodles, right? Noodles is good, but I just don't like noodles. I like rice because of the way I live my life. So we are not using pin, and most of our and all these things are purely data driven, right? We don't have any residual or any laws as a physics and others, basically. Reinhard?
So yes, I think if he has any follow-up question, I think he probably doesn't. So yeah, I would like to just ask a question, and if time permitting, just that most of the problems that you have shown, you have actually done a data-driven mapping. So two questions, basically, two subparts to this one question rather, that do you actually feel that incorporating physics would actually make it more trustworthy? So that I'll probably just put it as one question, that what about the trustworthiness of these models? So like you said that sometimes it doesn't work. Sometimes, for example, for a high Reynolds number case, it actually gave not so good results. So was it a case of extrapolation or interpolation? First question, that's a part rather. And then how do you think that these machine learning models could be made more trustworthy, and within quotes trustworthy? I really don't know what would be the metric to kind of really define trustworthy, but probably explainable is one way of doing that.
Yeah, I had a long chat with Shovik about these things because we were writing some proposal. So the thing is that, again, physics is great. Like we need physics, right? I think physics informed is actually kind of like a very established term. For example, like especially for the nuclear application, like if there is transient condition and very high irradiation, you can have empirical equation, but like nuclear reactors actually, like even if you think about the single reactor core for the naval reactors, they run for 30 years, right? And even the nuclear plant actually run for 60 years and others. So maybe and the nuclear plant, we have some cycle, like beginning of life, middle of life, end of life. So in the beginning of life, when the fuel is pretty fresh, irradiation has not been accumulated much, physics informed really works well. I have seen some work on that. Because the problem is not actually the physics informed or the machine learning. Because when the fission starts, initially your U235 get the fission, right? And that is fine. But after some time, you have your U238 to plutonium, and there are other things that transmutes daughter products. So all these things, if you can brought in your physics, their decay chain and others, then physics might work. But I don't think we are at least capable, like at least our team is capable in doing that, because we are not chemists, actually. Because those decay chains and the physics of decay chains, which are actually, again, you have to go to the energy level, energy diagram, and very fundamental nuclear physics. If those coupled differential equation highly, and we can further refine it and bring to machine learning, then only I believe it will work. I cannot guarantee. Otherwise, it's a bit risky, and it's not. I'm not answering that actually like on my behalf. And this is actually like at least 2 or 3 times I got that comment in my proposals, actually. So the problem of the physics informed, and to answer the second question, trustworthy. I really don't know what trustworthy means. I think it's a relative term, at least to me. Because again, I can trust you, but the person I know for 20 years, I trust him more. The person who is my dad, I trust him more. So, but I trust my dad more. It doesn't mean that I don't trust you, right? So trustworthy is a relative term. So when we're talking about AI trustworthy, at least for the energy systems, physics can make things better. But again, like I don't have any proof, like at least for my applications. Like for my applications, maybe there are many papers that proved it, but not me. So I really cannot comment on that. Again, to answer your question in a single word, I think physics should make it trustworthy, but accurate physics. not just putting any physics, any loss function. Again, as I said, if you want to have the middle of life condition, 15 years in the in the naval plant, naval reactor, then is it really easy to capture all the physics? I don't know. Like it's crazy. Like it's at least like 100 pages of equations maybe. Right. So I think that gonna make it complicated. When the fuel is fresh, you can do that. I think most of the physics informed work are actually mostly for when the things started. But I think we need more foundational work when the things really get complicated, right? So that's why I think I have no idea how it works.
Yeah. No worries. I think Souvik will have a question.
Yeah, so thank you. So I will conclude it. I think we're out of time. So I concluded one very small question. I mean, other things I can discuss with you anytime I want, right? So one of the things you mentioned was control, right? Different aspects of digital twin. And one of the things was in the context of nuclear reactor control.
Yeah.
Now, in infrastructure control, the way I understand can be vibration control, or in aircraft, it can be the motion control or whatever. In nuclear reactor, is it the process control or what control are you talking about here?
No. So when in the nuclear reactor, it's actually like, it's a very good question. In the nuclear reactor, we are talking mostly autonomous system as control.
Okay.
Because the new reactors that hopefully will come, micro reactors, those are not actually like land-based. Those will be mostly in, for example, in Siberia or Alaska, maybe in the operational battlefield. So can we control them remotely with human insight? That is actually more on the control rather than the control you mentioned.
Autonomous decision making and all those things.
Autonomous decision making, exactly. This is the most control side of the nuclear. Okay. And that's where actually, like, I think I had a chat with you that agentic AI actually jumps in.
Right. Yeah. So I think with that, we'll conclude this session. Next week, we have another session by Professor Romit Maulik, and he will be talking about AI plus fluids, AI and with some climate flavor. That's next Wednesday, same time. And I will obviously circulate it. And if you have already subscribed, you will be receiving an email also with the poster and everything, right? So till then, goodbye. I hope this is useful. I will be putting it on the YouTube channel as well, maybe after some edits or, and that will also be accessible to anyone. Okay. So with that, let me thank Professor Alam once again. I think we have a meeting also. So yeah. So
thanks, Professor Chakraborty.
Thank you, Professor. Yeah.
Take care.
See you.
Take care. Bye.
Have a good day.
Yeah. Bye. Thank you, everyone. Bye.
Bye, everyone.